We've got some data, and these data are two variable data, x1, y1, x2, y2, etc., through xn, yn. And what we'd like to do is we'd like to use these data points to make predictions about what y is for some other value of x. Goal, use these data to make predictions, or you could say estimates, about y when you know x. That's the goal. Then the question is how? This is all a modeling kind of thing. There are different methods. How? If the data seem linear or close to linear when graphed, in other words, when you graph these points, they seem to lie close to being on a straight line, then use a linear model. In other words, a linear function. Say y equals L of x for linear. What's a linear function? As in calculus, it would be, I could write mx plus b here. In statistics, it's traditional to not use m and b for the slope and intercept, but instead to use b sub 0 for the intercept and b sub 1 for the slope. That's the intercept, and that's the slope. And there's a good reason for using those. The main good reason for it, there's other good reasons for it. The main good reason for it is that maybe even on Thursday, we're going to generalize this to maybe like a quadratic model or a cubic model or a fourth degree model. We won't do all of them. And if we do such a thing, it'd be good to be somewhat consistent in our notation. Like if there's an x squared term, maybe its coefficient should be b sub 2. If there's an x cubed term, maybe its coefficient should be b sub 3. Okay, it's for consistency's sake. That's probably the best reason. Well, so what do you do with this? How do you decide what the intercept and slope are? That's the crux of the matter now. You define for each value of I between 1 and n, for each I between 1 and n, remember n is the number of data points here, something called EI. This E is not the number E, not the number E. It stands for the ith error, E standing for error. Actually, it's kind of funny. It's more often called the ith residual, but we prefer using E for the symbol. It's the actual value of the second coordinate of the ith data point minus the predicted value. Actual second coordinate minus predicted second coordinate. We're talking about y values here. In other words, y sub I minus, what's the predicted second coordinate? Well, I'd have to use my linear model. I guess it would be L of x sub I. I should have been using cursive, somewhat cursive x's all the time here, but I'll try to from now on. Not that you have to, I just, it's been traditional for me. Whatever L is, if the data are not exactly on a straight line, which in general they're not, this is going to be what we call the error. And that's actually a general fact when you're making estimates in math is to say the error is the actual value minus the approximation or prediction. And it's fortunate that actual comes before approximate in alphabetical order, right? Actual before approximate. Yeah, you want to do actual value minus predicted approximate value, or I could also do observed minus predicted. Instead of writing the word actual, I could say observed second coordinate. And that's also fortunate because observed comes before predicted in alphabetical order. Oh, how great. That's the order you want these things. But what is L of xi? Using the formula for L, I guess it's B0 plus B1 times xi. And then distributing the minus sign through, I guess this gives yi minus B0 minus B1 xi. Okay, what do you do with this? It'd be nice if all these e's were small, right? Close to zero. Now, sometimes your prediction, your L value is going to be too small. It'll be less than yi, making this residual positive. And sometimes it'll be too big, making the residual negative. You would hope you get a bunch of small numbers, some positive, some negative. Maybe they should average out to zero. How could you make them small? Choosing B0 and B1 in a good way. Now you could try to eyeball it. What's the intercept? What's the slope? You could draw a line in there. Or you could be more scientific about it. We want to be more scientific about it. We want to minimize SSE. What's SSE? Sum of squares of errors. Sum of squares of errors as a function of the unknown intercept and the unknown slope. A function of two variables. Well, what is it? What's a formula for this? Sum, I guess I need a summation sign. I guess one term for each data point, a sum of squares of errors, sum of squares of residuals, I guess EI squared. Where each EI depends on B0 and B1, so I could write this. Why do I square these numbers? Because if you didn't square them, some would be positive, some would be negative. You'd get a SSE close to zero. It wouldn't really be an SSE in that case. Maybe even exactly zero, and that doesn't make much sense. If all the EIs are close to zero, whether they're positive or negative, then when you square them, you also get a bunch of numbers close to zero, but they'll all be positive. That's easier to work with. You might say, well, maybe I should take absolute values instead of squaring them. And that's possible, but to tell you the truth, nobody likes working with absolute values. So we compromise and we square them, right? You don't like absolute values. No, actually, I do like absolute values, but I'm strange, right? Most people don't like absolute values. They just feel confusing to people. So let's square them. That feels a little bit better. And if we want to minimize this, maybe we need to differentiate it. Yeah, I don't want to differentiate an absolute value. And that is what we want to do. We want to now differentiate this. It's a function of two variables. I need to compute some partial derivatives. We skipped the example of maximum likelihood estimation in chapter 7 where there were partial derivatives, but I'm not going to skip it here. Remember, B0 and B1 are unknown. The X values, the XIs and the YIs, those are given numbers. I want to differentiate this with respect to B0. So I need to differentiate with respect to B0, that thing. Derivative of a sum is the sum of the derivatives. I can bring the summation sign out in front. differentiate this with respect to B0. Treat everything else like a constant. I guess it's an application of the chain rule. Bring the 2 down in front. And then B0 is in there as a negative B0. I guess I need to differentiate negative B0 with respect to B0 to give me negative 1. And those two things are constant with respect to B0. They differentiate to 0. I guess this is the derivative of SSE with respect to B0. What do we want to do? We're trying to minimize. I guess this is a calculus problem, optimization. I need a critical point. Take the derivative, set it equal to 0, solve, set this equal to 0. But wait a minute. How am I going to solve for B0 and B1? That's 2 unknowns, but only 1 equation. Well, I need another equation from differentiating with respect to B1. Let's do that next. Let's differentiate SSE with respect to B1. If you're not used to partial derivative notation, by the way, with the cursive looking D, don't worry about it. It's not a big deal. I could have used an ordinary D. It's just convention to use a cursive kind of D. Just to highlight, hey, we're doing something a little extra fancy here. We're doing partial derivatives. So let's use a fancier symbol just for fun. So now I'm differentiating with respect to B1, treat everything else like a constant. Once again, the derivative of a sum is the sum of the derivatives. Once again, I need the chain rule. I get a 2yi minus B0 minus B1 xi. And now the derivative of that inside function with respect to B1 is not negative 1, but negative xi. I got to set this thing equal to 0. So this gives me a system of 2 equations in the 2 unknowns B0 and B1. Dare we try to solve for B0 and B1? Yes, I dare. Should you dare on the test? You probably won't have to, but this will be helpful when you take applied stats to be able to think this way. Boy. We've done this kind of thing before with, maximum likelihood estimators, working with summations like this. I can cancel the 2's. The 2's can go away. I can also distribute the summation sign through. It's a property of summations, which is really, ultimately, it's related to the commutative property for addition, that I can do that. So what happens if I do that? I get, for the first equation, the sum. Oh, by the way, I'm also going to shorthand notation from now on. Just a plain summation from now on means sum from 1 to n. Okay, just to save some writing. So the first equation now becomes sum yi. I will keep the subscripts as i's when necessary. Minus the sum of, I forgot to bring the negative sign through. Negative sum of yi plus sum of B0 plus sum of B1 xi, and I'll factor out the B1 equals 0. And for the other equation, I got to multiply through by negative xi. I'll get a negative sum xi yi, and then a plus B0 can be factored out, sum xi, and then a plus B1 sum xi squared equals 0. Keep track of what your goal is. I'm trying to solve for B0 and B1. Should seem like a good idea to simplify that. I is going from 1 to n here. That's our convention. So I'm adding up n B0s there. That's the same as n times B0. Maybe the terms that don't involve B0, these 2 terms should go to the other side with a plus sign. So I get n B0 plus B1 sum of the xi's equals the sum of the yi's. That's the first equation. And the second one's going to give me B0 sum of the xi's plus B1 sum of the xi's squared equals the sum of the xi's times yi's. This system of equations has a name. It's called the normal equations, but it has nothing to do with normal distributions. It's normal equations for regression. And yes, once again, you want to solve for B1 and B0. I'm going to just solve for them right now. It's worth seeing this once in your life if you are going to apply statistics on the job. Let's see. I think I'd like to eliminate B0 first. So I'd like these two terms to have the same coefficient for B0. So I'm going to multiply the first equation by the sum of the xi's, and I'm going to multiply the second equation by n. So I'll get n times the sum of the xi's times B0 plus B1 times, if I multiply that by the sum of the xi's, I get the sum of the xi's squared. If I multiply that by the sum of the xi's, I get the sum of the xi's times the sum of the yi's. The second equation, I multiply everything by n. N times sum of the xi's, B0. Multiply that by n, I get plus nb1 sum of the, careful, I guess I don't need parentheses here. The squared goes inside the parentheses. I mean, it doesn't hurt to put parentheses, but it goes inside. And here I get n times that thing. And what I'm going to do is I'm going to now subtract to eliminate the B0s. I'm going to subtract the, a little funny, I'm going to subtract the first equation from the second. So I'm putting the minus sign up there. Yes, a little funny. These cancel. When I subtract this minus that, the B1 can be factored out. Like this. And when I subtract this minus that, I get this. And I won't bother with parentheses over here on the right, but it's understood with these terms that you do the summations first before you multiply them. And then finally, B1 therefore is n times this summation minus the product of these summations divided by n times this summation minus this summation squared. Understand what's going on here. For example, in this summation, you're doing x1 times y1 plus x2 times y2 plus x3 times y3, etc. Here in this summation, you're adding the x's, and here you're adding the y's. Do the addition before you multiply the summations. In other words, find the summations first. Here you are adding x1 squared plus x2 squared plus x3 squared through xn squared. Here you're adding all the x's first before you square the result. Okay? That shouldn't need much more explanation for you guys. Statistical analysis students need a lot of practice with this. So that's B1, and if you look in your book, this is the formula for B1 that you'll see there in chapter 11. What about B0? Let's take this first equation and solve for B0 in terms of B1. I will subtract this from both sides and then divide both sides by n. So I'll get B0 is sum of the yi's minus B1 times the sum of the xi's, all divided by n. And that can be split into the difference of two fractions like this. That's convenient because now that's y bar minus B1 times x bar, means y bar and x bar. Do I need to plug in the formula for B1 into there? Well, you could if you wanted to, but I don't really see a reason to. Figure out B1 first, then use this formula to figure out B0. You should be able to use these formulas on the test. And when you put the data into your calculator, the summations are given if you do two variable stats. Quick example. And here's the example I'm going to do. The example I'm about to do is just for fun. It's not a good application of linear regression. I'm going to, for my x values, use 1, 2, 3, 4, 5. Whoops. 3, 4, 5. And for my y values, I'm going to use the corresponding first, second, third, fourth, and fifth prime numbers. 2, 3, 5, 7, 11. Not a good application of linear regression, because if you graph these points, they're not linear. Lots of people try to use linear regression when they shouldn't. I'm not advocating that in doing this. I'm doing it just for fun and to show you that it's bad at predictions if I let n get bigger, if I let xi get bigger. Just to illustrate, it's bad. But I'm going to do it anyway, just for fun, to illustrate the ideas. So now going to my stat menu again, going to calculate, go to two variable stats, list 1 and list 2, calculate. X bar is 3, I could use that here. The sum of the x's is 15. Sum of the x squareds, we need that now, is 55. You've never needed that before, probably. Well, unless you use the shortcut formula for the variance in chapter 6. There's standard deviation of the x's. We never use the sigma. Remember, a couple people use sigma on the test. No, don't ever use a sigma from a calculator in a test. In my class or Dr. Wetzel's class. You could be given a sigma on a test, but don't ever use a sigma from your calculator. Never, never, never. N equals 5. There's y bar, there's the sum of the y's, there's the sum of the y squareds. Okay, let's write some of these numbers down. There's the sum of x times y. So let's go ahead and write these numbers down. Should be able to do this on the test. So x bar is 3. The sum of the x is, which is really the sum of the xi's, is 15. The calculator is being a little more sloppy than we were. Sum of the xi's squareds is 55. And is 5. Y bar is 5.6. Sum of the yi's is 28. Sum of the yi squareds is 208. And the sum of xi times yi, it's down there, 106. As an example of one of these, 106, for example, is 1 times the first prime plus 2 times the second prime plus 3 times the third prime plus 4 times the fourth prime plus 5 times the fifth prime. Should check that you get 106 there. 55 plus 28 plus 15 plus 6 plus 2. I won't do it in my head. Now use the formulas. B1 is that. So B1 is going to be n is 5 times the sum of the xi's times yi's. That's the 106. Sum of the x's is 15. Sum of the y's is 28. Divided by n times the sum of the xi squareds is 55 minus the sum of the x's quantity squared. So this is supposed to give us the slope. 5 times 106 minus 15 times 28. And the top is big number, 222,000. Oh, did I do times? Okay, thank you. Didn't seem right. 110. And then 5 times 55 minus 15 squared is 225. It's 50. Hey, nice number. 11/5. That's 2.2. And then B0, the intercept is y bar minus, y bar is 5.6, minus the slope we just found, 2.2 times x bar, which is 3. 5.6 minus 6.6 is -1. So our regression line has equation y equals L of x equals -1 plus 2.2 times x. And if we were foolish enough to try to use this equation to predict the 50th prime, we'd be way off. In using it to predict the 6th prime, we would compute L of 6 and get 2.2 times 6. What's that? 13.2 minus 1 is 12.2. Obviously not a prime, but not too far away from 13, the 6th prime. Right? Am I counting my primes correctly? 2, 3, 5, 7, 11, 13. The E6 would be actual value minus approximate value would be positive 0.8. That would be the observed value of that if I use the regression line to make a prediction. Not too far away from 0, a fairly small error, but the errors would get worse if I try to use this for the 7th or 8th or 9th or 10th prime. It would be a bad formula. So don't use this to predict primes. Okay? There are other things worth mentioning here, and then we'll end class today by looking at this on a spreadsheet. Just on the tip of my tongue, what's another thing worth mentioning here? Another thing worth mentioning here that I find easier to remember is that B1, the slope, I in my mind often represent with what I write as SSXY divided by SSXX. When you do regression, there are lots of SS's, which as in SSE stands for sum of squares. And SSXX stands for a true sum of squares. This sum of squares, it's once again understood that I goes from 1 to n here. I'm using the shorthand, just a plain old summation, but the convention is I goes from 1 to n. That's a true sum of squares. Now, the SSXY is actually not a true sum of squares, but we go ahead and use the SS symbol for it anyway. It's the sum of two products that are different, so it's not a square. It's the sum of this product. And then I happen to remember, just because I've taught introductory statistics so much, that these summations can be expanded into the following summations that look like this. That for the top and this for the bottom. But when you look at this, it doesn't look like the exact same formula for B1 that we had. Right? I've got fractions within fractions here. It doesn't look the same. But it is. Just multiply the top and the bottom by the same thing to cancel the ends. And lo and behold, you get the same formula that we have. So I'm teaching you this just because, in part, because that's how I remember this formula. And I think it's a worthwhile thing to think of it this way. And sometimes another reason to know this is that sometimes in software, whether it's a calculator or a spreadsheet or something else, some other statistical software, sometimes you might be given these SS values when you do something. And so it's nice to know that you can compute B1 as just a plain old ratio of two individual numbers that might be in your output in whatever software you're using. Let's end class by looking at a spreadsheet here and do as much as we can in the time that we have in a spreadsheet. On Thursday, we'll also use Mathematica. Let's do the same example. Primes, again, I am not advocating this as a good application of linear regression. If I was after the regression line as quick as possible here, the quickest way to get it is to highlight the data values, insert chart, and pick a scatter plot. And that's the default here, is a scatter chart. And in the, I think it's the series option, you can also add the trend line, which is the regression line, and show what's called R squared. What is R squared? It's called the squared correlation coefficient. We don't really need to worry about what that means at the moment, but I like to do it anyway. Okay, so here we have it. There's the quickest way to get the line, or to at least see it graphically. The slope is supposed to be 2.2, and the y-intercept is supposed to be -1. Now this is 1 here. 0 would be over here. If you follow this line down, it's supposed to have a y-intercept of -1. Does the slope look like it's 2.2? As x increases by 1 from 1 to 2, y is increasing, it seems, from about 1.2 to, yeah, 3.3, I say. Right there, that would be a slope of 2.2. Notice that some of the points are below the line and some are above. When they're above the line, actual value minus approximate value is positive. Positive errors when the point is above the line. When it's below the line, actual minus approximate is negative. The actual value comes from the data point. The approximate value comes from the line. So we had 3 negative residuals and 2 positive residuals that do average out to 0 in terms of those residuals themselves. But when you square them and add those results up, you get the observed value of SSE that is minimized. If I didn't, and you don't see the equation of the line here. I think if I didn't have the R squared there, it'd give me the equation. Maybe if I make this bigger, it'll show the equation. I thought it usually shows the equation. I'm not sure why it's not showing the equation there. Maybe I shouldn't have done the R squared. If I'm after the equation of the regression line as fast as possible without just inserting a chart, here's what I'm going to do. I'm going to make some labels here. And one of the labels is this unspecified correlation coefficient. I'm actually about to show you another formula for the slope that gives you the answer as quickly as possible based on what I'm about to do. And it helps to interpret the meaning of the slope more than the formula that I showed you. I could just do equals SUM for the sums. It's not necessary to compute these sums with the formula I'm going to show you, but I want to do it anyway. I can divide those sums by 5, or I can do equals average to find the means. 15 divided by 5 is going to be 3. 28 by 5 divided by 5 is going to be 5.6. Did I not copy and paste? There we go, 5.6. Standard deviations are going to be computed as well in this quickest way of getting the slope without the formula from the book. Equals correl with 2 R's and 1 L will compute something called the correlation coefficient. Is that related to correlation back in chapter 5? Yes, it is, but I won't say how. And the quickest way to get the slope of the regression line from these summary statistics that we have here is one more formula for the slope. The slope also happens to equal the correlation coefficient, which is labeled with an R. Back in chapter 5, it was labeled with the Greek letter rho. Remember rho? R, rho is the Greek version of R. R is the data correlation coefficient. Multiply that by the ratio of the standard deviations, SY divided by SX. That is another formula for the slope. So when I use that formula here, if what I've told you is correct, it should give us 2.2. Notice the formula, how I'm using it. B11 is the correlation R. C10 is the standard deviation of the Y's. B10 is the standard deviation of the x's. Yep, 2.2. Same answer. Okay, I think that is worth showing you. Do you need to know it? I'm not saying yet. I will talk about how this is useful for interpreting the slope on Thursday. Thursday is going to be all about interpretation and some fancier spreadsheet output and ultimately inference without using the crazy formulas in the book in section 11.2.